Okay, so it's already 5 minutes past the starting time, so let's get started. So today it's a pleasure to have Santos here, who is a coordinating professor at ISEL and an invited professor at the University of Lisbon, where he is a researcher at the Center for Theoretical and Computational Physics. He was a postdoc at Royal Holloway, University of London, put in by FCT, and then Marie Curie Fellow at the University of Southampton. And he focuses on Higgs boson physics, extensions of the standard model, symmetry breaking, dark matter, and vacuum structure. He convenes the CERN group on neutral extended scalars, and he received the Premio de Excelência by IBL CGD in 2018. And so today he'll tell us about CP violation at the LHC.
Okay, thank you. Right, so I'm going to tell you about CP violation at the LHC. Let me see where I will stand. I will stand here. And I will start by, I will talk about CP violation in a lot of different contexts, from tree-level processes to loop processes. And I will try to show you that some of these processes come from C violation and other processes come from P violation. And this will mean different things when you look for the process at the LHC. There will be theoretical parts that I will try to pass fast, and then we'll go to the more experimental things. Okay, so these scalar extensions of the standard model have been studied a lot because they provide dark matter candidates and new sources of CP violation that are needed for baryogenesis. They change the di-Higgs production transaction, for instance, and they provide a means of having a strong first-order phase transition, something that is not possible in the standard model because the Higgs mass is not small enough. Okay? That's why we need some extension. And they provide a Higgs that is compatible with all data. And then, of course, you get a lot of extra scalars, and so everybody is happy because they're moving for the extra scalars. Okay, so some of the things I'm going to talk here that started a long time ago. For instance, there is this these angular variables. Wait. Okay. Sorry. Yeah. Good. Okay. So there are things that people are doing for a long time now. And for instance, one thing that started, well, at least preparing for looking for the CP number of the Higgs in the coupling, in the coupling to the tops. Okay, so you see there's a TTH coupling here, and this coupling, we know already that the Higgs is not a pure CP-odd scalar, but it can have but it can have a small component of CP-oddness. Okay, and so what you have to do is to find variables, and this is one of the variables that is used, for instance, in this process that was measured both at ATLAS and CMS. You have to find variables that will tell you the CP odd part from the CP even part, so that you can measure what is the CP odd component that is there. Then there are other things that you could do. There is, for instance, this combination of 3 decays that I will explain later, that if you would see 3 different decays, like we already saw this one, so if you would find another scalar that would decay at the same time to ZZ and to another Higgs and the Z, this would also be a measure of the CP violating sector. I will come back to this one. And then there is also this scenario that I will also discuss in more detail later, which is the following. Suppose that you find a particle, a 200 GeV scalar, and now you're going to look for this, for the decays of the scalar. And of course, this cannot be the standard model. Sorry about this. You decay to TT bar or to tau plus, tau minus, and these two, if you then measure the CP odd and the CP even component, this one could look as, for instance, CP even in the decays to some fermions, and it could look as CP odd in the decays to other fermions. So this is a very strange scenario for CP violation, because it's not two particles. This is exactly the same particle that would behave differently in the two cases. Okay, so in everything I will discuss here, I will use just one benchmark model that is called the complex version of the 2HDM, because it's really the simplest scalar sector that you can have with CP violation. So that's why we're using this model for everything, because we want to know where we can go with the simplest version. So what is the difference between the two potentials? So this you know already, you saw this many times. It's a standard model potential. This is the SU2-Higgs doublet. When you have this field, you know that you end up with a standard model Higgs boson and 3 also bosons. This you've seen many times. Why am I talking about this? Because this potential does not allow for C or P violation either explicitly or spontaneously. Okay, so because these are phi squareds of phi dagger phi, you cannot violate C, you cannot violate P, you cannot violate C. Okay, so this is something that you cannot do in the standard model. So that's the reason I'm showing this, is because you have to at least add another doublet so that you can do it. Okay, so this is the two-Higgs doublet model. Why? This is the most general two-Higgs doublet model. Instead of one field, we have two fields now. Instead of just one vacuum expectation value, usually we use two vacuum expectation values. We could have decided that we don't want this vacuum expectation value. If this was the case, then this would be dark matter. Okay, if we take D0, because we could keep this Z2 symmetry exact. If you keep the symmetry exact, you can have dark matter. But we're going to put the V2 there because, unfortunately, this model cannot have, at the same time, dark matter and CP violation. Then you have to extend it a bit more. And so we're going to focus on CP violation. How do you do CP violation here? In a very simple way, you take M12 squared and then the 5 complex, and this is enough to have explicit CP violation. And of course, if you have a, so for those of you who are not used to this terminology, explicit CP violation means that you break it in the Lagrangian. Spontaneous CP violation means that you break it in the Lagrangian. Of course, once you break CP violation in the parameters, it doesn't matter if your vacuum breaks CP violation or not, because CP violation is already broken. Okay, then you can. There are a lot of ways that you can then couple the fields, these two fields. So if you still remember how to build the Gauss Lagrangian, you take these two fields and you couple them to the fermions. And the way you can couple these two fields to the fermions with the Z2 symmetry is just these 4 types of models. So this one, type 1, is where you couple only one of them to all doublets. You use a symmetry for that, so that the model is renormalizable. For instance, you say that the up has this symmetry or the down has this symmetry. And so when you put them together, in some cases you can put them together, in some other cases you cannot put them together. Okay, and the important point is that there are 4 different models. This is type 1, this is type 2, which is the famous one because it's the one related to the MSSM. And then you also have another two possible combination. This one is called flipped, and this one is called lepton specific. Now, regarding the couplings are not that different. They have the same Lorentz structure. So if you remember the coupling of the Higgs to the gauge bosons, you have this coupling multiplied by some sign of angles, it doesn't matter what they are, and you get the 2HDM coupling. And if you go to the complex version, you also get just another factor. So all these modifiers, the power couplings to the gauge couplings, are just functions of angles. Okay, so they are extremely simple in that sense, and also in the sense that there is no other Lorentz structure. You could expect that this would be very different, like it happens for the Yukawas, which in the case of, and I will come back also to this later, in the case of the complex two-Higgs model, you get something that is very standard model-like, but then you have a gamma 5 component here, and this gamma 5 will tell you that there is CP violation, as I mentioned. Okay, so this is what you need to know, that in all these scalar extensions, the Yukawas of the new model are either just a function times a standard model, or something with the gamma 5. Okay? And if you have these two at the same time, this means CP violation. Here, even if you have CP violation, you cannot see it in the coupling. Okay, and the same for the scalar. You look at the couplings, and the couplings look exactly the same. So you have no idea, when you look at just the coupling, if there is CP violation. So we need some other way to look for CP violation in these cases. Okay, what is there is just a number times the standard model, or a number times the standard model. Here you have a different Lorentz. Once in a while, I will talk about the alignment limit. And the alignment limit is a limit where all couplings to a chosen scalar are exactly the standard model ones. So in all models, there is a limit where the couplings are, at least of one of the Higgs, are exactly the standard model ones. If the model does not have an alignment limit, then it would be very hard, because the data we have so far shows that we are very, very close to an aligned scalar, right? Because every coupling that we've measured so far seem to be very close to the standard model. Okay, I will go fast here. This is just to tell you what are the differences what are the differences between couplings that are CP violating or P violating. So, very quickly, these are the C transformations. The C transformations, so this is a quantum operator, so we just have to see that you apply the operator and then you apply it again and you get a 1. So this means that this C squared is equal to 1, which means that the eigenvalue is either 1 or minus 1. Okay, this is basically what you need to know about charge conjugation. The operator is the operator that changes the particle into its antiparticle. And for the P transformation, you just change the spatial components. So you have covariant, contravariant change. And of course, then you have also the possibility of having a plus and a minus. And the same thing for any other scalar. The only difference are for spin 1/2 fields, because now here you see you have the current. It's a current that is P or C conserving or violating. So these are the transformations for psi bar psi. They are always the same for P, C, and CP. In gamma 5, there is a minus sign there, but C is the same, and the others for the vector gauge bosons are also the same. Okay, so this is the part that I will not tell you much more in detail, but let me just tell you how we know that something comes from P or from C? So first of all, you need to know two things. The first one is that if you have a renormalizable theory, if you want to have one, you need to have at most dimension 4 terms in the Lagrangian. Okay? Mass dimension 4 terms. What is the dimension of the operators? The dimension is you have this is a gauge boson. These are the spin 1 and spin 0 particles have all mass dimension 1. How do you know that? You take the action, you take the Lagrangian, and for instance, you probably remember Klein-Gordon equation. What do you have in Klein-Gordon equation? You have a derivative, and then you have a phi, and then you have another derivative, and then you have a phi. These four things need to be dimension 4. Means that each one of them has dimension 1. Okay, and that's why this here has dimension 2, and this here has dimension 2 as well. Okay? And so if you want the more general thing, you can write this kind of terms, and this means that the parity of the Higgs boson is 1. Okay? And I'm not, there's a lot of things that you need to know to understand what's there, but one thing that should be clear is that if you deciding the parity of the Higgs has to be done with its interactions with other fields. Okay? This is how you do it. You don't know in the beginning. You start with 1 and then you go on and find. So why do we know that the parity is 1 here? Because independently of what the parity of the Z is, this is Z squared, so it's 1. So why do I say that then H is also 1? There are two possibilities here. Either the Lagrangian is invariant for parity, and then you multiply 1 by 1 and you get 1, or the Lagrangian is not invariant for parity, and then of course H can be whatever you want. So you start by saying, I want the Lagrangian that is invariant for parity. C squared has parity minus 1. It's parity 1. H has to be parity 1, so 1 times 1 is 1. Okay? And of course, then you can do the same for charge conjugation. And what you conclude, I will just go to the conclusion. What you conclude is that it is possible if you have vertices like the ones there. So remember that to fix the parity of the charge conjugation of any particle, you need to see its interactions with other particles. And so what you see here is that the charge conjugation of a scalar has to be minus the charge conjugation of another scalar if you have couplings like this. So couplings like this are not allowed, and if you follow this analysis, you see that in the absence of fermions, invariance under P is guaranteed. Okay, so whatever the scalar extension of the standard model we have, if you have CP violation without the fermions, it comes from C violation and never from P violation. Okay, and this will set the scenario for how to look for CP violation. Okay, so in the standard model, we know what happens. This is known for a long time. The C of the photon is -1. The P is also -1. And by construction, the Z, remember that if two things mix, they need to have the same quantum numbers. So if we know the C and P numbers of the photon, we know the C and P numbers of the Z, because they mix by construction. And if you put everything together, you will see that the C of pH is also 1. In this case, the P of pH is 1. And as for the Goldstone bosons, the P of G0 is 1, and the C of G0 is -1. Okay, so this is the standard model. Let me very briefly tell you what happens in the 2-HDM, in the complex case. So you have these two doublets. These two fields will mix. One of them will give the Goldstone boson, the charge 1, and there will be a charge Higgs. I don't care much about what's happening here, but from the degrees of freedom here, which are 4, we have 4 fields, 1, 2, 3, 4. You can have either these 4 particles, the boson, it has to be in both cases, and then you have what usually is called small hv, h and a, or h1, h2, h3. In this case, we're talking about the CP conserving model. In this case, we'll be talking about the CP violating model. This is just related to the m(2) squared and lambda 5 being complex or not. Okay? Now, this spectrum here includes 3 neutral scalars. You see h1, h2, h3, and they are ordered by mass. Okay, so this is the lightest, this is the heaviest. If you have, for instance, these 3 Higgs, you see that if this is p invariant, then it's 1 times 1 times 1. If it was -1 times -1 times -1, it would be -1. So this means that if I have a vertex like this, I know the p numbers of H and I know the c numbers of H. Okay, and so these are all CP eigensets. But now you ask me, okay, so if I need to look at the vertices, then how do I know that a model violates CP via C violation? Okay, so let's take these 3 mass eigensets, H1, H2, H3, and of course, because they mix, they have the same numbers. And now you look at the interactions, whatever interactions give you the right numbers. So let's take H1, H2, dz. I know that these are interactions, I've seen them, they are there, okay? Otherwise I cannot conclude anything. And then you have H2, H3, dz, and H1, H3, dz, okay? Now, dz is p invariant. Why? Because d transforms from covariant to contravariant, and z transforms also the other way around. And so this term is invariant under p. So this means that for this to be CP conserving, in this case C conserving, because let me tell you again that Z has C minus 1, so you would need a -1 here to multiply this -1 for C. So C of H1, H2 would have to be -1. The C of H1, H3 here had to be -1, and the C of H2, H3 had to be -1 as well. And of course, this is impossible. Okay, so if you look at the Lagrangian and you see that these vertices are present, you will conclude that the model is CP violent. In the scalar sector, we've not started with the fermions yet. Okay? Good. So another possibility is to look at things inside the loop. So sometimes people ask, why are we measuring at the LHC triple Z anomalous vertices? They are also, they could have CP violation inside. And how do you know that? Because you can write this kind of vertex, assuming only coherence and invariance and U1 electromagnetic edge invariance. You can write it like this. This is the operator, and this operator is also P conserving, CP violating. So you can have a CP violating vertex related to what is going on inside this model. Now, of course, in the standard model, this term is 0 at one loop, because there is no CP violation in the standard model without the fermions, as I'm talking here. And also, even with the fermions, you usually need to go to 2 or 3 loops. So, but in other models, we could measure F4Z, and this has been done by both Atlas and CMS. So let me tell you exactly what we would be looking for. So there are a lot of different possibilities, because if we go back, this is always related to what I just said here. So I've chosen 3 vertices to show you that there is CP violation here, but I could have chosen a lot of other different vertices. But it's the combination of these these vertices, when you put all the three together, that signals CP violation. If you have only two of them, you cannot conclude anything, okay? So you always need three. So let's look at, for instance, this one. Because, why this one? Because this one will really be the simplest of all. You would have H1 decaying to ZZ. H1 would be, for instance, another model one. If you would find another scalar, and these new scalars would have these two decays, this would mean that the model had CP violation. So it's a very strong statement. There is a problem with this statement, and I will tell you later why. Let me just get, there's no watch here, right? So that I have an idea of what's happening here. Okay, so then the others are of course just combinations, other combinations, and will not tell you anything new. Okay, so recently we decided to see if these scenarios were still possible. So as you know, there are a lot of enthusiasm now about di-Higgs production, because of course di-Higgs can tell you something about what you can, about the shape of the Higgs potential. And so we decided in this very simple model, because of course if you can see something in this very simple model, you can see probably in other models. And what we did was the following. We combined, we already have of course the H1 to ZZ. So what if we had another Higgs decaying to H1, and the same Higgs decaying to H1Z? Of course, this would be a sign of CP violation. We have looked if this was still possible with all the constraints that we have now taken into account, and indeed it is. So the search, this is an extra motivation to search for specific channels in the di-Higgs, because if you see these two these particular channels, you will be saying that there is CP violation in the model. Of course, these are all for resonant production. Okay, so then of course you can suppose that you find nothing. You can say, oh, okay, I can do much more combinations of these triple vertices, and I can go. I can pretend that we'll be having a muon collider in 100 years, and we just played with this center of mass energies and this luminosity, because people aren't these days talking about this muon collider a lot. So we thought, okay, let's see if, because why? Well, why am I saying this? Because it could be that at the end of the high luminosity stage, we could be so much close to the alignment limit that everything else would be zero. For instance, this H2 to ZZ is forbidden in the exact alignment limit. So this means that the more H1 is standard model like, the more this coupling is zero. Okay, and so it's getting more and more difficult to see. So that's why at some point, because we found a set of vertices that are also allowed in the non-alignment limit. So we decided, okay, let's see what we can do. As you will see from the diagrams, I mean, this is very hard to do at the LHC. We thought about doing this, but look, it's a Z, H2, and then H3, and then H3 has to decay to H2, H3, and also this type of diagrams, or this type of diagrams. It's already bad enough to look at this kind of VBS with the H plus H minus. So imagine with the H plus H minus and another HI. Okay, so this is almost impossible to see at the LHC. It's not completely impossible. And so we decided to see, I mean, this is a new one or click, a muon collider or click would be a much cleaner environment. Still the cross sections are very small, but indeed it would be possible, even if you would not see anything related to CP violation at the LHC, it would be possible to see it in future colliders for the same model. Of course, much harder. Okay, so just a caveat to finish this part, which is for. Now, the reason we don't write this vertex for the standard model because we know that it is not a CPO scalar, right? So AZZ is not allowed in a CP conserving model. And that's why we, as soon as we saw the Higgs decaying to Z, we thought, okay, it's decaying to Z, so it's not a pseudo-scalar. At least it has a small pseudo-scalar component, because the vertex is forbidden. This is allowed in a CP conserving model, but they are both allowed in CP violating models. Now, the problem with the standard model is that, of course, you could have, or any CP conserving extension, is that as soon as you have fermions, you could have this decay of a pseudoscalar to 2Zs. So this is allowed at one loop. When this is allowed at one loop, it means that it is allowed, but it's very small. How small? So what if this coupling, this three-level coupling, is so small that it's comparable with this coupling at one loop? Then you cannot decide. What do you do then? Well, you have to go back, look at the decays of the Z leptons, and then try to find again if this is CP equivalent. Okay? Good. Now, this is from P violation. No, okay, yeah, still, sorry. Okay, so now when you have all these decays, suppose that you like to have the 3Higgs with CP violation, you would like to put them all together, and you would like to look for these decays, but you, of course, at this time in your life, your people that are working in particle physics are depressed because you find no other scalars, so you go home, you feel depressed. But one way of not feeling depressed is to imagine that they are inside loops, okay? Because the Z's are real. And when you build a diagram like this, you have, look, it's the ZH1H2, the ZH2NH3, and the ZH2H3. So this is putting all these decays, but together inside the diagram. Okay? And so maybe you don't see the Higgs directly, but you can see them inside this beautiful red diagram. Okay? And are the experimentalists looking for this? Yes, they are. But let me first tell you about an even stranger thing that can happen. When you do the 2HTM, you can add another term. And so you know when you have a visible sector and a dark sector, usually you call the term that connects the visible with the dark sector, you call it portal term. And suppose that you have this symmetry, you may believe me, will give you dark matter candidates. Now, this is a portal term, it's a CP conserving portal term, and also this one is a CP conserving portal term. But you can use this term here, and this is a CP violating portal term. If you do this and you put no VEF here, then this Z2 symmetry is preserved, and there will be 3 dark matter candidates. And what is interesting about this model is that you will have 3 dark matter candidates, and at the same time you have CP violation in the dark sector. So not only these type of diagrams can tell you about CP violation in a normal model, let's say with no dark matter, but it can also tell you about CP violation in a completely invisible sector, okay, because they could be still inside the loops. And so we decided to do the calculation. And this is something that was done for the combined doublet model. This part here, and this first of all, this, if you remember when we started, I told you about this F4Z, that this was a part of the Lagrangian that would measure CP violation. Okay? And this was in the beginning, so maybe you forgot by now, but there are ways to measure this. This is done by the invariant mass distribution of the four-lepton system, okay? And this will limit the triple Z and two Zs and one gamma couplings in DP2ZZ. Okay, these are the results from 2018 from Santos and CMS, and this is the more recent results from CMS. It is improved by 1 order of magnitude, and it's not that far away. So if you look at this what you can measure, what you obtain from the models is something that is close, not there, but close to 10 to the minus 5. Okay, and the bounds here are 10 to the minus 3, and here are close to 10 to the minus 4. So it's getting closer to have something to say about CP violation inside the triple Z. So I expect that, well, during the next run, we'll reach the 10 to the minus 5. Okay, let's move to P violation. And same thing, I'm just stopping here to show you that why this vertex is CP violating. So you see, the vertex is, suppose that you have a phi, right? The couplings with C do not change. So they are here, C transformation the same. So this coupling here, all this, is C conserving because these C's plus 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 are the same. But they are P, the P changes sign. Okay, so this means that if I put the phi there, whatever the values I choose for C and P, this will be CP violating because the currents together transform differently for C and P. Okay, so this is always a CP violating vertex. If you put them inside the loop, you can also look at this term. This is also P violating CP violation. Okay, so what have Santos and CMS been doing with this pattern? Well, the first measurement, the first direct measurement, and I think this is a landmark in the direct searches for CP violation, was done with the TPH with H going to gamma gamma. Now we also have H going to BB bar, and you see here the measurements of the P odd and P even components, and you see that this is like a blob here and here. This is the best fit, and this is of course very interesting, but it's not as important as the other measurement, which was the taus. But first, let me show you just why all these things appear as these lines here in this plane, maybe. So if you consider that this is the CP even axis and this is the CP odd axis, if you have a coupling that is A plus IB gamma 5, this means that if you just look at the rate, you square it, and so this gives A squared plus B squared between two limits, okay? And that's why you have this circumference here. Okay, so you always, when you look at these plots, also from the experiment, you will always see that there is the plots always have this kind of shape, as you see here. Okay, so this is exactly what was done for the tau. Why is the tau so important? Because the top is so heavy that the couplings to the Higgs will we already had a feeling that the CP odd component was really small. But with the taus, it was not like that at all. And the importance of measuring the couplings to the taus is, I will just come back to this, but I don't know if people that usually went to CERN 3, 4, 5 years ago, there was this idea that everybody was wasting their time doing these direct measurements because EVMs were telling us that we don't need to do them, which of course was silly. Because not only it was silly just because it was silly, because direct measurements are always direct measurements and they are better than the others, but it was silly because it's wrong. Okay? You see here that this is, I will explain this in more detail, but this is the allowed region of parameter space in, again, the same axis. And this is allowed with all the EDMs. Okay, and this region was cut because of the H2 searches. If they were not there, this would still be allowed by the latest EDM results. Okay, so it's of course important to go to these scenarios. Okay, so now one thing, why am I so interested in this part in particular? Because at some stage in our life we realized that there was this weird possibility that you would have the same particle behaving as a scalar in one place and behaving as a pseudo-scalar in the other place. And this was exactly the case. We presented this case, well, to motivate further the searches, the direct searches for the CPO components of the pseudo-scalar. And of course, you could ask, is this possible in any model? And of course, it is possible in the complex version of the 2HDM. You just have to play a bit with the angles, and after playing a bit with the angles, you realize that this is indeed possible, and you can have coupling like this and another one like this. There is a gamma pipe missing there, and of course, then you can look for them. This was the first plot we did a long time ago, and you see here what we're saying is basically this: even without the results from direct searches from the top, because as I told you, the top is so heavy that it was already very constrained. It had to be very, very CPO'd, the coupling with the top. CP, sorry. And so this is the coupling with the top, and it's close to 1. And if this point is allowed, then this behaves more like a pseudo-scalar in this case, because this is the place where the CP even component is 0 and the CPO component is 1. Okay, so this is a very strange thing, but possible to look for. So this is what I've shown you already. So what we did very recently was look for all the possibilities in the C2HDM to see if this kind of weird scenarios were still possible or not. We published something in 2017, and now this is something that just came out with the new experimental data. So what is new? We have here all run through the data collected at 13dV. Of course, there are also the data from searches for additional scalars. The EEDM was changed from 8.7 10 to the minus 29, this value, and then more recently to this value. And there's also updates on the bound of the charge X mass. But the most important thing is the impact of direct searches and the ones using angular correlations in the decay plane of the tau lepton that is setting an upper limit for the pseudo-scalar component. Okay, so let me show you what happened. So this is when you go from 2017 to 2024. So remember that we have three neutral scales, H1, H2, and H3. H1 is always the lightest, and H3 is always the heaviest, which doesn't mean that H1 is the 125. Any one of them can be. In fact, what we saw for this type of models is that taking the H1 to be the 125 was already excluded, and so we started using all the other possibilities. Because in principle, any of them can be the standard model. The differences between the old and new data and the new EDM bound light and dark. So light is the old, dark is the new, and the color code will be the same for some of the other plots. Okay, so there's nothing that dramatic here, but there is here. So here, in this case, these are both from 2024, and there are no constraints from searches from extra scalars on the left, and on the right, these constraints are taken into account. So you see that sometimes you think, okay, this is just about the Higgs, but if you put the other, since all these scalars and the angles are linked in somehow, it means that, for instance, because this may be very weird, the point is the following. If you want to avoid the electron dipole moment, you need, for instance, the masses to be very close to cancel this. And so if they need to be very close, then the searches for extra Higgs could fill that part. Okay, so what we put this plot, and we like this plot exactly because there are a lot of things coming together to allow or disallow what we have in the models. And also, there's another point here, but this point is not only is much more difficult to explain, but it's also something that we don't know yet what to do with it, which is these EDMs are things that are calculated at 1 and 2 loops. And when you calculate things at loops and you have quark masses, you have to put running masses, and the running masses have to be chosen at a given scale, and if we choose them at one scale, we get everything excluded. If we choose it at another scale, we still get some points. Okay? So what do we have to say about that? Absolutely nothing. Okay. More scenarios. So this is the lepton specific, and you see here that the only point relevant here, because the rest is just the same thing, is exactly this. In 2024, putting everything together, we still have the red dark points everywhere. Okay, so the most constraining EDMs that we have today still allow for points everywhere, while the direct searches have cut these pieces. Okay? So this disappeared, and this strange scenario, at least for this particular case, disappeared exactly because of the direct searches and not because of the EDMs. So next time you are at CERN and people tell you about EDMs, you say, yes, that's very nice, but they will not constrain everything. And you can show them these slides, okay? Because there's still this idea that EDMs will rule the world, and they will not. Okay, so finally, what do we have here? We have the following possibility. So we decided to see, okay, what if we choose H1 to be the Sun model Higgs, and then H2, and then H3, is this possible or not to have these strange scenarios where you have the very large CPO component? So cross means that it is not possible to have this large CPO components. This tau means that the exclusion comes from direct searches for CP violation in H2 tau. And the underlying cross refer to scenarios that were previously allowed but are not allowed now, meaning this one and this one. Okay, so now you could ask, okay, so what about the other lookouts? Because I mean, from the point of view of a particle physicist, this seems very poor, right? Because we have done the top and we have done the tau. We still have all the others. For instance, the V. Why can't we do the V? Well, the problem with the V is that if we look at what we have done for the top and what we have done for the tau and try to do the same thing, we'll see that it is impossible. You don't have the mass of the B so small that the symmetry that you see in the top, you will not see in the bottom. Okay, so this means that you cannot see it in production. You could do the same. You can ask the same question. Can we do it for the B's as we have done for the taus, with the decays of the taus? And the answer is no. I mean, these people did it in 2021, and they said that even at the 100 dB collider, this will not be possible. I mean, maybe in the future we can refine this analysis and find a way to do it, but so far it's the top and the taus. And there are people trying to do other stuff, but they're not that interested. Okay, so let me just finish with the CP violation from loops. And you could ask, should we look? So the question here is the following. Suppose that, again, we have this type of operator, which means that there would be a CP violating term in the coupling to the doublets. Okay, so this would be the CP violating term. And you could ask yourself, well, but is it worth it to look for CP violation in HW doublet? And in the standard model, CP violation comes in 3 loops, and so the answer is no. Okay, this is like 10 to the minus 20 something. So it's there's no way you can reach this number. This is what we have now from the measurements. This is from 2016, 2019, and there's one from 22. And these are the numbers. So these are the latest numbers. They are of the order of this times 10 to the minus 3. So let's say 10 to the minus 4 at most, the present reach. And so we just did the same calculation in a CP violating model to see if 10 to the minus 4 was an interesting number. And it is, because you see in the CP violating model, the same model, you get the largest possible value is 6.6 times 10 to the minus 4, which means that indeed this is close to what is being measured these days. Okay, I'm just finishing, because I think this is enough, with something that I've been working with people from me for a long time, but this is the first paper I published with Carlo and Patricia. And so we are doing the same thing, but now for a tree-level process and look for the effective operator. That is exactly the same as I showed you before. This was done already, but well, Carlo and Patricia are doing most of the work, so they can tell you what they're doing. So one of these days. Okay, and to finalize, the main message is that direct searches for these CPO components is important. Gives information that cannot be obtained with EDMs. Unfortunately, only tau and tau were probed until now. And this combination of this data, including EDMs, has shown to be crucial, because also the searches for new scalars, when combined, for instance, with EDMs, having the mass to be close together, can give you some interesting information. And also, another very important point, this is the final message that I want to leave here, is that standard model measurements are the starting point to probe the ISEL models. Because sometimes it seems that they are not yet relevant, but they are extremely relevant, because they are the starting points to know if the ISEL exists or not. Okay, thank you.
Okay, let's take a break.